Hello, my name is Ed Sharp and I'm a research associate at the UCL Energy Institute. This is a virtual lecture as part of the Smart Energy Systems module on an introduction to modeling electricity demand and supply in Python. So I'm going to start off with a few slides introducing Python, what it is, why would you use it, a couple of examples of what the uses are, a brief description of the pros and cons, and then I'm going to go into some practical examples. The first one is just to explain the data structures and how you set it up, etc. And then I'll go into two case studies. The first, how to model demand from heat pumps in the UK, and the second, how to model demand from some simple wind turbines. And hopefully just give an overall introduction and allow you to move forward if you want to use Python. So to start with, just the description of what Python is. So essentially what it is a programming language. And because it's a programming language, in order to use it, you're going to have to learn or improve your skills if you already know a little bit in command line programming. Pretty much everything you want to do in Python, you're going to have to write out in a piece of text or code. It's the same as every other programming language in that way. What's slightly different to other programming languages is it's quite high level. So there's a lot of stuff going on behind what you're going to write down when you write an algorithm or a plotting piece of code or whatever. The advantage to that is that you don't have to write a lot of code. The disadvantage is that you maybe don't know what's going on underneath, and also that it can be a little bit slow. So within an academic or university context, Python is a data analysis scientific software. So it's used a lot for collecting data from various sources, harmonizing and storing that to a certain extent, and doing analysis. Part of that kind of analysis can be producing plots and graphics. Very good tool for that. You can quite quickly learn how to do publication level plots, for example, and you can then, once you've learned how to do that, repeat those very easily, adapt them, etc. It's quite an important tool for GIS. Part of that is because ArcGIS, which is the sort of industry standard big piece of software that does everything, is written in Python, and you can export all of the algorithms that you would run in the graphical interface in ArcGIS into Python, which means that you can automate those processes, you can loop through, you can do batch processing, which is a really powerful tool for people who want to do GIS. It's definitely a modeling tool, primarily because you can run loops, for example, and this kind of thing, but also allows you to do anything that you would with any other language in that respect. We'll go through another example of that. So apparently it's named after Monty Python. It started in 1991, so it's been going for quite a long time. So why would you choose Python? So a big reason is the fact that it's free. You don't need a license, it's an open license, and you can download it very easily, which means that having learnt it, you should be able to continue using it whatever you go on to do. In contrast, for example, if you use MATLAB, which is also a good option, but if you went on to be doing something in a company or on your own, you would have to pay to be using that, unlike in the university. Whereas with Python, you can go away and continue to use it forever, in theory. Cross-platform, which is quite important. So it'll work on a Mac, and it'll work on a Linux box, and works well with Windows. There's not a lot of changing the code between those things. Might have to do a little bit to do with data retrieval and working through file systems, but it works well on all of them. It is easy to learn, but only as programming languages go. It's very good because it tells you in sort of fairly plain English what it thinks is wrong in your piece of code when something goes wrong, which is really nice. And it forces you to set out code nicely. So you'll see in later examples, you have to have indentation for code to work, where a lot of other times you don't have to have that, so things can look a little bit more messy. It's very well supported, particularly online. So if you have a problem or you're a little bit stuck, something like that, you can quickly ask questions online and find help very easily. Most problems which you come up against will have already happened and therefore been answered. There's also a lot of users within our university department and likely to be elsewhere. It's increasingly used by people. The data structures are excellent, particularly with arrays. I'll show you in an example, but they make a lot of sense. They're easy to access and manipulate and apply algorithms to, unlike some other programming languages where you have to do a lot more and able to do the things quite simply. This is really important in data analysis and modeling. I think I've already gone through the GIS stuff. So why would you not use Python? A big reason is the fact that it can be quite difficult to install and maintain. There are different versions and different modules within those versions, and the simple way is to install a pre-prepared package, but that package may not be set up in the perfect way, and it's quite difficult to adapt that. It's not an insurmountable problem, but it does make it slightly harder to use than something like MATLAB, for example, again, which is all set out for you already. You just download it and it works and it'll be updated. So you have to have a little bit of skill in order to be able to run it yourself. But again, there's people that can help. If you're doing simple stuff, it may be an unnecessary level of complexity. It's definitely possible that what you want to do is much easier in Excel, and if you know how to do that already in Excel, there might not be a reason. But I would encourage people to at least try, because it very quickly gives you a greater level of capability. As mentioned before, it can be a little bit slow, so if you're doing very complex things, it's often accepted that doing something in C or even Fortran is a better idea. But you can translate to that, so if you get good at Python, you can write it in Python and change it. And whilst to say it's very widely used in universities, I've written it's not very widely used in consultancies, but it depends where you go. I kind of feel like Excel would still be a pretty standard thing across all industry, but if you can do Python well, Excel is easy, so you're doing yourself a favor. So how to get started with Python? There's a few different ways to do it. So definitely the easiest way to do it, as I said before, is to download a pre-packaged distribution. Canopy is a good one, which is from Nthought. I'll show you the link later on. I'm going to give examples in an IPython notebook, which I think is a really good place to start with this because it's well set out, etc. You can also run it in a command line or even within other GUIs such as ArcGIS. But today I'm going to do all the demonstrations in IPython notebook because it's a nice way to do teaching, etc. But once you get used to using that, you'll very quickly figure out the other ways. So that's the slide section of the presentation. So the rest I'm going to do in IPython notebooks. So as mentioned before, I'm going to do the rest of the presentation within the Python environment, just to show you how it works and hopefully give a bit more of a practical explanation of what it is. So this is an IPython notebook. The IPython notebook runs within a browser, which is really good. Works in different browsers, in this case Chrome. And it's just a place basically where you can write and run code. It's very useful because it sets out things in boxes and lets you go back and change them. And it's just very neat, basically. It does so. There's a couple of different ways that an IPython notebook are going to run. So if you download one of the packages that I mentioned earlier on, including Canopy, I'll just show you where that is. So you can download this if you work in a university or you've got a university email address, including if you're a student, you can get it for free. This will download the whole of Python for you, including Nthought, but will also allow you to run the IPython notebook. Alternatively, there is increasingly extensions which allow you to run this kind of notebook without having installed it. An example is this Chrome extension, which this isn't a very good link, but you'll be able to find a proper one if you just search for this. So the advantage of the full package is that it gives you more capability, and it gives you the ability to alter those packages, whereas the extension will only give you limited capability. But if you're just looking to try it out, maybe the extension is the best option, but it shouldn't be that hard to get a hold of the package. So to start this IPython notebook, assuming that you've downloaded one of these Nthought packages, you just go into your terminal or command prompt, depending which operating system you're using, and you type in IPython notebook, and that will launch the browser with showing you your file system, and then you just have to open a new IPython notebook. I'll provide a copy of this notebook so people can work through and get their examples of how to do this. So to run the code, you're basically going to write in one of these boxes and press Shift Enter to run whatever's in there. These boxes can be different things. So for example, this top box is code, right? Text. So you'll go to the cell type and you'll define it as Markdown. If you see an example, if I change the code, it will change to commented, but I want it to be Markdown, so I'll call it that. So there are two. If you're going to write in Markdown, you can just write text. That's fine. If you want to write text in a code box, then there's two ways you can get it to be text. One way is to put it after the hashtag symbol, and then anything after that is commented out. The next way is to put it between 3 parentheses, and that's another way to write comments. So the next step when you're running a piece of Python code is to import the necessary modules, and these modules contain the code that you will need to run everything. Some of them might already be in there, but it's good practice to have a box at the top which imports everything. So an example we're going to be using in this workbook is NumPy. So I've already typed to import NumPy, but something else we'll be using is datetime, and you just type that, Shift Enter. The starter notes that it's running, and it's run. So this is another Markdown text, and you just need a hashtag symbol and it will be a title. So I'm going to start off with showing you examples of the different types of data container in Python. So if you kind of relate this to what you might be used to using in the Windows Office, for example, you're going to be looking at different ways to fill out a spreadsheet, for example, whether you're going to be putting in a list of values or a two-dimensional array like a spreadsheet type thing, and then other ways of storing it. So the first example is a series, right? So the example here is I'm just going to type out my variable name, which can be anything you want. In this case it's my list, just to make it obvious. And then you're going to open a pair of square brackets. You notice that when you're using IPython Notebook, if you just type the first of a square bracket, as in also in different types of brackets, it will actually fill out this next section for you. It's very useful, but be careful that you don't put things in the wrong place, which is very important. So let's just create a simple list of values. So this is creating a list 1 to 8, and it's going to be in with these square brackets. So you've created that variable, and let's just, in order to call the variable later on, you're just going to type in the variable, and it will show you what you've got there, right? So that's a very simple example. There's your list. You've created your first list, and you've put some data in there. So in order to call that list, the first thing you can do is obviously what I've just done and write down my list. But you also in Python have very powerful ways of calling certain elements of that list. And the first example is just to be calling a single element of the list. So this is how to call the first value in that list. 0 is what you use in Python, not 1. Note that. So calling the first value 1. There you go. Just to show that you can call them in the right way. This is going to be the fourth value, 3. Okay. So another way of selecting values is to select a range of values from your data container. That uses the following syntax. So I want to call the first to the fourth value, the first 4 values in that list. I want 0 to 3 with the this symbol in the middle to call that. Okay, 0, 1, 2, 3. There you go. This also works without putting values at the beginning and the end. So if you leave out the value, if you don't put a value, it assumes it goes to the end. And that works in the opposite way as well. So if you assume that, then it assumes it comes from the first value. So just to make that clear, I'm going to copy that down here. Show 3 to the end. Okay. So that's list. That's the simplest data container in Python. Something that you're going to use a lot if you use Python, so it's important to understand it. So lists are always one-dimensional, and if you want to start stepping into something a bit more complex, then you're going to have to learn how to start using arrays. So in the same way, I'm going to create a simple array and show you how these things work. You're going to go back to this module we imported at the top, NumPy, because that is basically an array module. And the way you do that is to say numpy.array, which is basically saying, rather than a list, I want this data to be stored in an array. You can open it with curly brackets this time, square brackets, oops, wrong ones, and let's have a simple one where you're 1, 2, 3, 4, and then another row with 5, 6, 7, 8. See what that looks like. So you can see you've added another dimension. You basically stack these two single lists on top of each other to create a two-dimensional array. So you can use the same methods for indexing. Let's call this first value again. So in this case, you're not calling the first single value, you're calling the first set of values because it's this two-dimensional array. And in the same way, you can call the second set of values. So now you've got this extra dimension, you'll be able to call things by columns and rows. So you just called a row there, and let's show you how to call a column. So you use the following syntax. Let's call the third column. So you see you're extracting this column of data, the 3 and the 7. You can call multiple columns in a similar way, using similar syntax, but instead of having a single column in this position, you have a range of columns. So 0 to 2. And the right, this is 0 to the second value. So you've got the first and the second rows. So a pretty basic introduction to arrays. You'll hopefully get to understand this a little bit better when we go through the examples. You can also do structured arrays, whereby when you define these structured arrays, instead of calling the columns by number, you can call them by a name reference. I'm going to skip these because it's not really in a basic introduction, and also you can use other ways to do that. So as I mentioned in the slides, one of the powers of Python is the ability to perform operations in arrays and lists quite easily. You've seen this sort of indexing, but there are also a couple of other things you should learn straight away, and that's how to add data, for example. So in terms of a list, you're going to append some values. Just to append a single value, split value, use this syntax, and you're going to change your list to now include a 9. You can put anything there. You can put a range. Put a range this way. Or if you wanted to add a series of numbers, you'd use a loop. So when you're coming to do adding data to an array, it works slightly different. You can use hstack and vstack. So you come back to NumPy and you say numpy.vstack. Use the following syntax. Call your, say what you want to add. You want to use your array, and then stack some values on the bottom of that. So let's say 9, 10, 11, 12. When you're using something like vstack, you're going to have to use something in the same dimensions as the rows above it, otherwise it's not going to work. For example, if I tried to do this, it would tell me that it can't do it because it's not the right size. So there are a bunch of different ones of these. This is a simple introduction. You've got hstack and concatenate. These might come up in the examples. Otherwise, this just shows you the general way to do it. And if you want to learn how to do extra things, I would suggest going online, and don't want to spend too much time on this in this presentation. I'll just show concatenate quickly. Concatenate. So this is where you're just going to add stuff in a different way to your array. I'm going to put my array in again. Use the same thing as this. But now you want to add another row. It's telling me that it has a problem with the number of dimensions. That is because this needs to be a single form. There you go. So as well as adding values, you can perform operations on the values. So let's go back to my list. and do a very simple mathematical operation, multiply everything. No, yeah, what happens when you do times 2? You're actually getting -1 and then you're adding -2. If you're going to try that with your array, you're going to come out with a different form. So let's go back to my array, multiply that by 2. Instead what you're getting is all the values in the original array multiplied by 2. So you're seeing that it's quite simple to apply these operations. You've got quite simple functions, but you need to know what those functions do. Another example is you take my array, and rather than times it by a singular number, times it by something of the same dimension. Times it by itself. And again, you times in 1 by 1, 2 by 2, 3 by 3. So that's sort of a basic introduction to what you can do, the simple things. Hopefully these things will become more clear once we go through the examples. You've got, the list. With the list and array, you can already do quite a lot of things. And so far in these, I've just been entering integers as a simple example. But you should be aware that there are different types of data type as well as data storage. So just as an example of that, I'm going to make a list with floats in it. Just a simple example to show that data can be stored in different ways. It's a good example also of the fact about syntax, because in some ways you would think that you could use a comma there, but actually commas are separating values and points within the value. So very similar format, just a different thing inside there. An important thing to note with floats is that if you don't use floats in divisions, you're not going to get the right answer. 1 divided by 2 is not 0. So you have to use a float in there in order to get the right answer. This is very important when doing mathematical operations, etc. And just a quick example, you can also do characters. These have to be within speech marks. And this is the problem I was talking about before about IPython Notebook creating the ending for you. Be careful. Jar list is not defined. List and equals. Show that file out properly. There you go. So as well as the simple data types, there are more complex ones. One of the most important, or probably most important, is a dictionary. And the way a dictionary works is to store your data as a key, which can be anything you want, and then a variable. So you're saying A equals something. To give an example of that, let's just type out a simple dictionary and store the arrays and the list we've done with some other data. So I'm going to call the key is going to be array, and you need this followed by definition of your variable. And then if you want to add something else to that, let's call add the list, the name of the list. And just to show that you can have different combination of keys and variables, I'm just going to have a key of 1 and the associated variable with another number. So there you go. So like I said, these are keys here, and these are the variables. So when using a dictionary, you can call these things individually. So if you take myDict and you want to know what the keys are, you use this syntax. It will give you a list of the keys. You note that it doesn't come in the order that I wrote it in. Dictionaries are not ordered, so you have to be careful when you're calling these. You can have an ordered dictionary, we might come to that later on, just be aware that you can. You can also show the values with the brackets. There you and you can call it by an individual key. So let's see what's stored in the key 1, 12, or in the key under the key array. It's a really powerful way of storing information. You can call it easily, and the values can be any mixture of things, and you can have nested dictionaries as well. So finally, just before moving on to the case studies, I want to just introduce a couple of important things for modeling. One of those things is dates and times. So like NumPy's, actually I did this before, just to give you an example. You have to import the datetime module in order to use these. And I'll give a better example of how these things work later on, but just for now to show how the format of these things, let's show what the date time is right now. Obviously this is now and I recorded it. And you've got a year, a month, a day, an hour, the minutes, the seconds, and the fraction of a second. And it's quite a powerful module because you can do things like export that as a string if you want to print it out, for example, or store it on a website, or anything you might want to do with that. And you can also use this module to import other data. So there's functions within there to say, I have a date and a time string in these formats. Please import it in a format that you understand, and then you can use that to loop through things, etc. We'll go through loops. And finally, I just wanted to mention pandas. It's a very important Python module which basically operates like a spreadsheeting function within Python. So you can import data into that and it will show you tables. I'm not going to go through that because it could take a whole hour to do, but just be aware that if you want to work in a tabled type structure where you can look at the tables fairly easily, pandas is your option. So that is the introduction to data types and data storage structures. Like I said, I'm going to put this sheet online so you can go through and have a play with it, and also, you know, you can go back and forward in this video if you don't understand something. So here is the first example of how to do some energy modeling in Python. The first example will be how to estimate the coefficient of performance of heat pumps across Great Britain. This is going to be on a gridded format for the whole of GB using half-degree grid squares, which is basically determined by the weather data that's going to be used to drive that. I'll show some examples, but the weather data is basically hourly temperature data for the whole of GB on a gridded basis. It's provided by Reanalysis, and those come in and get multiplied by a fairly simple equation, but this is just about showing you how to start doing a bit of simple modeling and then how to visualize it at the end to get some results out of your Python. So as in the last example, the first thing to do is to import the necessary modules in order to do the modeling. This is a much longer list than the last one, obviously, and slightly more complex, but essentially it works in exactly the same way. This is actually a more exhaustive list than will be used for the modeling, but it's just a sort of standard list that I import at the beginning of each model just to make sure everything's there. So as previously, Shift Enter, and you can see it working. Take a little bit longer this time, and the modules are imported. So the first thing to do is to import a little bit of data. So what is, because we need to multiply, we need to figure out the coefficient of performance based on temperature, and where those temperatures are going to be. This is what this model does. So the first thing we need is to get some data which shows the relationship between temperature and coefficient of performance. So there I've got a ready-made data set which is based on field trial data from the Carbon Trust on the performance of heat pumps in Scandinavia. So these are very high performance ones, but they're representative of what we might have in the future. So basically what this does is it defines a variable and then creates a NumPy array from a CSV file. This is what this bit of script here does. This is where the file is on my laptop, CSV file, and this is how the CSVs work. So just to demonstrate, if we import that HP and then see what that HP dataset looks like, and basically what you've got is temperatures in the first column in Kelvin and the coefficient of performance in the second column, and you can see when it's very low it's static and it increases over time. And just so it can be used in the model, I'm going to translate that into a dictionary because it's a bit easier to use. So basically what I've done here is define a dictionary, and then the way that you create is by zipping these two columns. You say, which basically this line takes the first column, which is this HP temperatures, like that, and the second column, which is the COPs, which look like that, and makes these the keys and these are the values as described in the previous example. And you end up with a COP dict that looks like this, if you've already pressed enter there. Keys and values. So just to demonstrate what that looks like, I could do a quick plot. We're going to use Matplotlib, and just to make sure that the Matplotlib, which is the major plotting package in Python, just to make sure that that goes in as an inline plot type this, and then very simply we take we're going to scatter these, we're going to plot the keys against the value. Keys. And values. And you can see this is the relationship. It's very simplified, but one between these temperatures. Let's put a text label. Y labeling, just to show that. So we've got our data, and we know that it's in the right form, so we plot it. It's always a good idea. Just a quick example of how to plot using Python as well. You can save these using this line, or you can just copy the image and paste it into your document if that's what you need. So we have a heat pump coefficients versus temperature, and another thing that we need for the model is land mask. So we need to know where the land is on our grid, and I've got a pre-prepared data set which basically has a mask of ones where there is land and 0 where there's nothing, and that's basically so if you multiply this array, as we saw in the last example, by the array showing our COPs, you make sure that there's no heat pumps being modelled offshore, which would be multiplied by 0. So I'm importing the land dataset using numpy.load, which works in a very similar way to the gen from text, but it's already in a NumPy format. So all I need is the location of the file on my machine. And just to demonstrate what that will look like, a very quick example of the reds are the ones outline of GB, and the blues are the zeros. So, and the final data we need is the wind data, which will be called within the loop of the model. So I'll explain that as I go along. So basically, by using three pretty simple data sets, you can start to create a little model of a heat pump coefficient. Obviously, the relationship between temperature and coefficient is quite simple. There are more complex ways of doing this, but this is just a simple example. So that now here, I'm just going to go straight into creating the simple model essentially. So what we're going to do to create a model of how it performs over time is use hourly weather values to drive that. So the hourly weather values are stored on the machine as arrays. So we need to figure out a way to call them. And basically the way that I've done that in this example is to go through a series of loops. Just a quick example of a loop is it goes for something in something, which would normally be a range of values. In this case, let's say for years in the range 2010 to 29 or 2050. And just to show that that loop works, I'm going to say print that simple value. Pretty much instantaneous because it's not doing anything, but that's showing you that how a loop works in Python. In this case, we don't actually want to do 40 years, we just want to do 1 year because we're going to do hourly values. And so we're going to go for years, and then for each of the month in those years, we need a month value for month in range. This range basically does between these values with an interval of 1. If you wanted a different interval, you can use a range, and then you just have to add another value, so let's say 2, but we'll use 1. We know there's 12 months in a year, so we can use that. And then for the day, for each day in that month, I'm going to copy a piece of code in this because it's just slightly complicated. And basically this is saying, this uses the calendar module, which I've imported up here, this one. And the way that works, or part of it works, is to say that in the ranges of these months, just to take the maximum day in that month, because obviously there's a different day in a month, so you can't have as in here, because it would say there's not these number of days in these months. And so I spoke before about how Python indents itself, and you have to use those indents in order for it to work. And this is an example of that in action. Because you've created a loop, this loop won't run unless it's indented. So let's show that again. So let's print the months this time for year, print month. So that's the months in 2010. But if I did this, it would still work. But if I did this, it won't print anything because it's expecting an indent. And this is a good example of the nice error reporting that Python gave that I explained before. So there's something wrong, and it does pretty much tell you it's because it's not indented properly. So you can look at the line that it's pointed out and say, okay, there's something wrong with that, let's try indenting it. Now it works. Perfect. So now we're going through, we don't really need this in this case, but I'll leave it there. So for this year, for each of the months in that year, each of the days in each of those months, we want to do something. We need one more step because we want hourly values. For our in range 0 to 24, because we know there's 24 hours in a day. In this case, it starts from 0 and goes to 23, as the loop always ends 1 before the value that you put in. And what I'm going to do is with that data is call the temperature data from my machine. So let's give the temperature data a variable name and figure out how to call it. So the location of the data on my machine is in this directory, but then the file names all have different names. They all start with tmp2m and then an underscore, and then the file names basically say tmp2m underscore year, month, day, hour, and after that, I'm just checking the format of them on the outside of the screen. Let's say .csv, .mpy. But obviously this changes for each of them, each of those, and these are in integer form rather than string. So we need to figure out how we're using this loop to call the data each one. And basically the format of that is to say, here's your string excuse me, for the start of the file name, and then you want to add something to the end of that string. And the way that works in Python is to put a plus there, and then to say you want to use your year value from here in there. But that's an integer, and Python doesn't like adding integers and strings together, so you have to make sure that it's in a string format, which is done like this. And you carry on doing that so then you have to put the underscore in between, which is a string. Perfect. And then carry on with the month. In this case, the month has to have 0. It has to be 0, 1, 0, 2, 0, 3. Whereas you can see here that they're coming out without that 0. So there's just a quick method to say to fill up to there to 2 values, which fills it with a 0. And so once you've added the rest of the string to that, you're getting missed out a little bit there, that's why it's all red. You're getting that. So that's set up to call the each temperature array, and that array is already in the same format as this array here, which is 74 squares long and 36 squares down, I believe. No, 80 and 34. So then you want to do something with this temperature. That's not all you actually. That's gives you the file name. You actually want to load it. So basically, as above here, you've got the NumPy load, and then you've got the string for the place where it is. This has just created the file name, and then this basically uses the same thing above, but sticks the file name in there. And I want to flatten that by reshaping the array. So I've got a single flat array, so I can loop through it easily. So the next step is to say for each each of the temperatures in that flattened array, which is essentially the same as a list. It makes it easier to loop through. I want to do something with each of them. And basically I'm going to go back to here, and I'm going to say for each temperature I've got, if it's in this list, if it's in this range of temperatures, then I want to find out what the COP is for there. And the way I have to actually just check. So the temperatures might be in a different format. This numpy around means just rounds them down to make sure it's in the same format as these things here, because as you can see, it's only to one decimal place, whereas the dataset stores it to a lot greater precision. And what I'm going to do with that is I'm going to create a new dataset which gives me the heat pump coefficient performance in the same format. So I want to fill that, go back to our dot append which we've learnt, and I want to fill that with the right COP from the COP dict. I'm going to say, and so I have to call it based on that, but based on the key that I explained before. So I'm going to go into this COP dict, and I want to say to get the value, I need to call from the key as described before. These are around brackets, and the way to call that is numpy. I'm taking this numpy around it. Yeah. And so you've got the loop, and what you're saying is if this number is in there, do this. But what happens if it's not in there? Good question. Let's put an else in there, which basically is saying if it's not in there, what else are we going to do? And what we're going to say is print a warning. The temperature is not in the range. Hopefully it won't come up, but at least if it does, we know what's happening. And as discussed before, we want to multiply this by the land dataset, because currently it's using all temperatures over this whole grid is figuring out the coefficient of performance. But obviously we're not going to have heat pumps out here in the sea, so we're going to multiply this derived range of COPs by this just to take that out. So let's just give it a new, it's in the wrong place, that's what I've read. Let's give it a new variable name, and then you want to multiply that by land. But as you can see, the land is not flat as this is because we reshaped it. It's in this grid still. So we're actually just going to reshape. We're going to need to turn this into an array first. Make sure it's an array, not a list as it was before, because it's been flattened. That's what you call a thing called numpy as array, just to make sure it's an array. And reshape it using the reshape command, as has been used to flatten it. You unflatten it to the same shape as the land. And finally, for each of these hours, in which each of these months, each of these days, we want to store this answer. So this is only for a single hour, as you can see at the moment, it's in this hour. So we want to create a dictionary, which we have to define outside of our loop, otherwise it will refresh each time. To store this information, let's call it HP results, and then we want to store something in these HP results. To store something in dictionaries inside a loop, you type the variable name, and then you type the key, we're going to go back to this method of taking the loop values and creating a string from them, and then we want the value for that key, which is this reshaped array multiplied by land. So we've basically now got our loop. So you loop through each year, month, day and hour. You grab the temperature data that you want, which is in an array form in a 34 by 80 grid. You load it from this place. You reshape it so we can loop through each value individually easily. And then you say for each of those values, what's the related coefficient of performance. You append this to this array, or list, and just a little warning there. And then just to make sure that it's only for places on land, we reshape this into an array, multiply it by this land value, and then save it. And once that's done, it loops back to here, carries on for the next hour. When it's gone through there, it'll go back to the month, and it's not going to do more than 1 year. So let's get the model running. Invalid syntax. So I obviously typed something in wrong there. Just to save time, I'm going to bring in the right one from another copy of this model I have. So it should work. That's not happy either. I've got an in. Temperature in. There we go. Another example of the nice Python debugging. Now it's telling me where it is and what the likely problem is. I've typed it wrong. That's the answer. And there you go. Model's running. I'm going to pause this whilst it's running to make. The model is finished running now. I paused it because it takes a few minutes to run. It takes quite a while to call in the data, etc. You can see that it's printed out each month as it goes along. But now we have this dictionary holding the values with the keys for the timestamps. So to just give an example of what comes out in the model, I'm going to just plot one of those timestamps and show you the results. So this is how to plot a figure properly. These last ones have been quite simple examples, and this one's a bit better. So we're going to define the figure and the size of it. We're going to add some axes to this. This is just an axis object, so you can control the figure. And we're going to use something called basemap, which is an example of one of the simple GIS things that you can do with Python. And this is basically adding the outline of GB and actually the whole world, but we're going to cut off the rest of that. And these are just some variables which says the lower left hand corner longitude is this, the lower left hand corner latitude is this, upper right hand corner long lat. The resolution, the projection, so that it matches the data from the array, and the axes, calling the axes object again. And we're going to go back to this IAmShows thing, which was used to plot here. I'm going to say on top of the map, we want to show the results from this timestamp. And we don't want to show the whole grid, we just want to show a section of the grid. And this is basically a slightly more complicated way of indexing, like I showed you in the last example. You're saying these rows and these columns, rows and columns. This is the color map that's going to be used, and this is the limit of the color map, just the color, the way that colors work in it. We want to tell the map to draw coastlines and countries. and we want to add a title which is the same as this string which is used to define the timestamp to record it from. And this is using the datetime module, and we want it to be in a nice format, so that's the way we're using that. Let's see what happens when we press that. Takes a little while, but there we go. Just add another couple of things to describe the map a little bit better. This is basically a legend, and a title for the legend. And there we go, this is what's come out of our model. So we've got the coefficient of performance between 2 and 4, which we can see matches our isolated static example, and we've managed to create a map to show for this timestamp the temperature according to our weather data, what the coefficient of performance will be across the country. What we're showing here is on the west coast, particularly the islands, we've got a very high coefficient of performance at this period in time because the temperature is higher, essentially. So this is very simple, but the key of the power of our model here is that we have stepped through a whole year to show what each point in that year would look like. So obviously we want to try and show that in our visualization, and the simple way to do that is animate it. You can do this within Python. I can show it to you, but it's better quality if you export the images and then use a different software to create an animation. So the way we're going to do that is we're going to go back to our dictionary in which we've saved the results of the model. We're going to say for each of the timestamps which we stored in keys, we want to call the value, we're going to call the data. And what we want to do is create one of these maps for each timestamp. So to save time, I'm just going to copy that code across, make sure it's tabbed in and indented, and rather than show it, we want to save it. So we're adding this plot.savefig line I told you about before, and this would be the place where you would want to save it. Let's just make sure it's saved in the right place. Obviously you change this based on your own machine. This is one of the differences between Linux and Windows I was talking about before. It's the way that file structure is defined. I copied this from Linux, and then what you're doing is saying in this location save each file, but so they don't have the same name, you want to add the date string on there, and you add that to the string that way. And to make sure they don't say all on top of each other, put a clear figure. So what I'm going to do is run this code, stop the sheet here, and then I'll show you the animation that results from this. Here's the example of what you get out of the model as a visualization. So you can see immediately that you get something reasonably powerful out of here. You can see how the COP changes over time and space, and get a good idea of where in the country you would get more efficient heat pumps or better use of the heat pump. Here in the western side of the country, you're going to get better relative energy out of the heat pumps than the rest of the country. Slightly different layout in this one because it was a previously saved one. If you want to watch the whole thing, just use the link above. It's still on YouTube. So I'm actually going to stop the presentation there because it's getting towards an hour length in time. I'll give the demonstration of the electricity generation in another installment. Thank you.